Right now, you know which way is up. You can feel it. The weight in your chair, the pressure in your feet, the floor holding you there. You've never questioned it once in your life. But leave Earth, and up doesn't just change, it disappears. Astronauts lose it within minutes. And yet our solar system does have a true up, a real precise direction. You could point at it right now. Nothing blocks it. There's no wall out there, no barrier, nothing in the way at all. In 70 years of spaceflight, almost nothing has ever gone there. Tonight, you'll understand exactly what's guarding that direction and why it's the one direction we still can't afford to take. Now get yourself comfortable, hit subscribe, we begin. Of all the things you believe about the world, one has never once been checked by you personally, never doubted, never examined, never even noticed. You know which way is up. You have known it since before you could speak. You have never confirmed it, never questioned it, and never needed to. It sits underneath everything else you understand about the world, and it left its fingerprints on the words you use every day. We look up to people we admire and look down on those we don't. Spirits rise and moods sink. Heaven sits above, the underworld sits below. Nearly every mythology humans have ever built stacked its cosmos vertically, gods overhead, the dead beneath, as if the universe had a ceiling and a basement. Even navigation encoded it. Every map you have ever held places north at the top, and though that choice is pure convention, it feels correct in a way that is almost impossible to argue with. We did not invent up as an idea. We inherited it as a sensation and then built a civilization on top of it. Now take that certainty and carry it into orbit. It collapses in minutes. The International Space Station orbits roughly 400 kilometers above Earth's surface, about 250 miles, which is less than the distance from Los Angeles to Las Vegas, just pointed vertically instead of across a desert. Aboard that station right now, a crew of people are working, eating, sleeping, and running experiments. And for them, up does not exist. Not up is different. Not up is confusing. Up is simply gone. Nothing aboard the station has a flaw in any physical sense. The modules are long cylinders lined on all four inner sides with equipment racks, and a crew member can work facing any of them with equal ease. Astronaut Chris Hadfield once compared the interiors to hospital corridors, narrow, packed, functional. But a hospital corridor has a floor you walk on. These do not. Engineers did give the station a working orientation. Most modules of the United States segment were designed with a designated deck facing Earth and an overhead facing away, and the station generally flies in what flight controllers call a local vertical attitude, one axis pointed steadily at the planet below. But here is what makes that decision so revealing. The orientation was chosen, not measured, not discovered, agreed upon, written into design documents, and painted onto hardware, because human brains work better with a reference than without one. A few modules, including several Russian docking compartments, attach perpendicular to the rest, and inside them, the floor runs at right angles to the floor next door. Now, run the thought experiment. Rotate the entire station 180 degrees so the designated deck faces deep space and the overhead faces Earth. For everyone inside, nothing changes. Not one sensation, not one measurement. No object shifts, no liquid moves, no body drifts toward a wall. The station's down was never attached to anything physical. Flip it, and the label goes with it. That should already feel strange, and the usual explanation for it is wrong. Almost everyone assumes the astronauts float because gravity is not there. Space is empty, so gravity must be absent. The logic feels airtight. It is completely false. At the station's altitude, Earth's gravitational pull still runs at roughly 90% of its strength at sea level. Put that in body terms. A person who weighs 70 kilograms on Earth, about 154 pounds, would, if you could somehow build a solid platform up at that height and stand them on a bathroom scale, still register close to 62 kilograms, around 137 pounds, 9/10 of their weight, still there. So why do they float? Because the station is falling, constantly. It has never stopped falling since the day it was assembled. Isaac Newton worked this out with a thought experiment more than 3 centuries ago. Picture a cannon on top of an impossibly tall mountain, firing horizontally. Fire it gently, and the ball arcs out and hits the ground a mile away. Fire it harder, and it lands farther. Harder still, and it travels so far that the ground curves away beneath it as it falls. Push the speed high enough, and the ball falls toward the ground at exactly the rate the ground curves away. It never lands. It falls forever, in a circle. That is an orbit. The station moves sideways at roughly 28,000 kilometers per hour, about 17,500 miles per hour, or 7.66 kilometers every single second, close to 4 3/4 miles in the time it takes you to say the word second. At that speed, it completes a full lap of the planet every 90 minutes, and the crew watch 16 sunrises and 16 sunsets in a single day. Gravity is pulling on them the entire time. They are plunging toward Earth every moment of every orbit. They simply keep missing. And a body that is falling has no weight. The floor is not pushing back because the floor is falling too. Remove that push, and something happens inside the body that most people have never had a reason to think about. You do not sense direction with one system. You sense it with 3, working together so seamlessly that you have never noticed them as separate things. The first sits inside your skull, your vestibular system, a set of tiny fluid-filled chambers and canals in the inner ear, lined with microscopic hair cells. When you tilt your head, the fluid lags and shifts, bending those hairs, and the bending generates a signal. Think of a half-full water bottle carried across a room. The water always finds the low side. Your inner ear is reading exactly that, continuously, from birth. The second is your eyes. They find horizons, walls, table edges, door frames, long straight lines that reliably indicate the vertical and confirm the answer visually. The third is proprioception. Pressure and stretch receptors buried in your feet, ankles, knees, spine and muscles reporting load. This is why you can close your eyes in a dark room and still know precisely where your limbs are and which way is down. Down here, all 3 agree. Every second, all day for your entire life. That unbroken agreement is exactly why you have never noticed them as 3 separate systems at all. In free fall, the agreement shatters. The inner ear stops reporting a direction because no steady pull exists to settle the fluid. The pressure receptors in the feet report nothing at all because nothing presses on them. Only vision still has an answer, and vision was never designed to carry that load alone. Imagine 3 witnesses who have given identical testimony every day of their lives, suddenly walking into a room where 2 of them fall silent and the third keeps talking. The brain has to decide who to believe, and for the first 2 or 3 days, it cannot. That confusion has a name: space adaptation syndrome. And despite what the word motion suggests in ordinary motion sickness, the cause is not movement at all. The cause is contradiction, conflicting reports arriving from systems that have never disagreed before. The symptoms are brutally ordinary and deeply unpleasant. Nausea, cold sweating, headache, disorientation, vomiting. Between 60 and 80% of astronauts experience it during their first 2 to 3 days in orbit, and a recent NASA medical briefing puts the broader syndrome as high as 70 to 90% of crew members. In a station crew of 7, expect 5 or 6 to be quietly, miserably unwell, some of the most rigorously trained and physically screened human beings on the planet, undone by a disagreement between their own senses. Spacewalks are deliberately not scheduled during those first days. The dominant explanation is sensory conflict, and the evidence behind it is strong. But researchers have not fully closed the case. A competing idea, the fluid shift hypothesis, points at something else entirely. On Earth, gravity holds a large share of your blood and body fluid in your lower half. Remove weight, and that fluid migrates upward. which is why astronauts in orbit develop noticeably puffy faces within hours. Supporters of this view argue that rising pressure inside the skull and inner ear could be altering the vestibular organs themselves, or triggering nausea through pathways that bypass the balance system altogether. Some early studies failed to support the fluid shift explanation, yet the question keeps resurfacing in the literature, partly because sensory conflict alone struggles to explain certain things, why the same conflict sometimes produces no sickness at all, and why vomiting is so common a symptom. The likeliest answer, based on current understanding, involves both, but nobody can run the decisive experiment because the only place the effect fully appears is in orbit, on a small number of people, at extraordinary expense. More than 4 decades after the first detailed studies, predicting who will suffer remains impossible. Eventually the brain solves it. Within roughly 72 hours, most crews adapt by quietly demoting the inner ear and promoting the eyes. Vision becomes the authority. Whatever surface you are facing becomes the floor, because you have decided it is, which produces one of the strangest experiences in human history. Charles Oman and colleagues at MIT spent decades documenting what astronauts call visual reorientation illusions, moments when the floors, walls, and ceilings of a spacecraft suddenly swap identities. A crew member floats from one module into another whose racks run a different way, and their sense of up rotates instantly to match. No movement, no warning. The room simply becomes a different room. For a moment, imagine you are there. You push gently off a handrail, drift through a hatch, and without your body moving in any unusual way, the wall in front of you becomes the floor. The colleague you are facing is now above you. Nothing physical changed. Your brain simply reassigned the direction, silently, the way it reassigns the meaning of an ambiguous word. Some astronauts report the room appearing to rotate around them when they open their eyes in the morning. Others, on spacewalks, have briefly lost track of where they were entirely. And when they come home, the whole process runs in reverse. The vestibular system, demoted for months, suddenly matters again, and for days afterward, returning crew members stagger, misjudge steps, and feel the world tilt when they turn their heads. Their bodies have to relearn a fact you have never had to learn once, sit with the implication, because it is larger than a medical curiosity. Your sense of up is not perception of a real feature of the universe. It is an agreement, a negotiated consensus between 3 biological systems, reached fresh every second of your life, valid only because you happen to live pressed against a very large rock. Remove the rock, and the agreement dissolves in under a day, which forces a harder conclusion. Up was never a property of space. Up is a property of nearby mass, and nothing more. Stand on the moon and up points away from the moon. Down there measures 1.62 meters per second squared, roughly 1/6 of Earth's pull. A person who weighs 154 pounds here would press into that grey dust with about 26 pounds of weight, less than a full suitcase. Descend into Jupiter's atmosphere to the level where pressure matches sea level on Earth, and up points away from Jupiter, a pull about 2.5 times stronger than the one holding you in your seat. That same 154-pound person would suddenly weigh close to 390 pounds, as though a second adult had climbed onto their shoulders and refused to get off. Different planets, different strengths, different directions, each one absolutely convincing to anyone standing inside it. And between them, nothing. No cosmic ceiling, no cosmic floor, no universal vertical running through the solar system that any of these local directions point toward. Up is not something the universe issues. Up is something you borrow from whatever mass happens to be pulling on you, and it expires the moment you leave, which leaves one question standing, and it is the one this entire story turns on. If up is borrowed everywhere, if every version of it belongs to some object you happen to be near, then what could it possibly mean to go up out of the solar system itself? There is an answer, a precise one, defined not by a planet, but by a shape almost nobody realizes we live inside. The shape has been in front of us the entire time, printed in every science textbook ever handed to a child, and drawn wrong in almost every one of them. Picture the standard illustration: the sun in the middle, planets arranged around it, usually at tidy angles, often scattered across the page like beads flung onto a table. That image teaches something without ever saying it out loud: that planets sit around the sun, in all directions, filling a sphere of space. They do not. Our solar system is not a ball with a star at the center. Our solar system is a sheet, a vast, thin, spinning plate of matter, and every planet, every asteroid, every human being who has ever lived sits pressed inside it. The reference surface has a name: the ecliptic. Strip the word of its mystery and it means one simple thing: the flat plane traced out by Earth's orbit around the sun over the course of a year. Draw the path our planet sweeps. Stretch a sheet of glass across it, and that glass is the ecliptic. Every other planet gets measured against it. Mercury tilts the most among the 8, running about 7 degrees off that plane. To feel 7 degrees, hold your arm straight out and look at your little fingernail. The width of that nail against the sky covers roughly 1 degree. Mercury's entire deviation from flat amounts to about 7 fingernails, held at arm's length. Venus comes in at 3.4 degrees, Mars at 1.85. And here the pattern turns strange, because the largest objects are the flattest of all. Jupiter, a world you could pour more than 1,300 Earths into, sits just 1.3 degrees off the ecliptic. Saturn, 2.49. Neptune, 1.77. Uranus holds the record, 0.77 degrees. Less than a single fingernail's width of tilt on a body 4 times Earth's diameter, orbiting nearly 3 billion kilometers out, around 1.8 billion miles. A distance light itself takes more than 2.5 hours to cross. Numbers in degrees stay abstract, so let's shrink the entire system down to something you could hold. Take Neptune's orbit, the outer edge of the planetary system, and squeeze it until it fits on a dinner plate about 28 centimeters across, 11 inches. A perfectly ordinary plate from a kitchen cupboard. On that scale, no planet in our solar system ever rises more than about 4 millimeters above the plate's flat surface, or sinks more than 4 millimeters below it, roughly 1/6 of an inch, thinner than the ceramic of the plate itself. Think about that for a moment. If you set that plate down on a table, the entire solar system would be flatter than the dish holding it. Astronomers, however, don't fully trust the ecliptic. Earth's orbit wobbles slightly over long stretches of time, and using our own moving orbit as the universal ruler carries a certain arrogance. So they use something better: the invariable plane. Every orbiting body carries angular momentum, the physical bookkeeping of spin, a quantity that captures how much rotational motion something has and which way it points. Add up every scrap of it in the solar system, and the total points in one fixed direction. The invariable plane sits at a perfect right angle to that direction, passing through the system's center of mass. Damya Sawami and Jean Suchet, working at the Paris Observatory, pinned down its orientation in 2012 to better than 1 millisecond. That unit sounds meaningless until you convert it. 1 millisecond is the angle a human hair would make if you held it up from about 11 kilometers away, nearly 7 miles. That is the precision with which we now know the tilt of our entire solar system. The answer: the invariable plane sits about 1.57 degrees away from Earth's orbital plane, and roughly 98% of all that angular momentum comes from just 4 objects: Jupiter, Saturn, Uranus, and Neptune. The Sun holds well over 99% of the system's mass, yet the 4 giant planets hold nearly all of its spin. Almost everything else, Earth included, contributes a rounding error. That plane does not drift. It holds its orientation across millions of years, like a memory the system cannot lose. Which raises the obvious question: why is any of it flat at all? Roll the clock back about 4.6 billion years, a span so long that no anchor from Earth's history can reach it, because Earth did not exist yet. No rock, no ocean, no life, no planet at all. What existed was a cold cloud of gas and dust, drifting in the dark, rotating almost imperceptibly slowly. Then gravity took hold, and the cloud began to fall inward. Here the crucial rule enters. Angular momentum can move around, passed from one piece of a system to another, redistributed, traded, but the total cannot simply disappear. Nature keeps that ledger balanced. So as the cloud shrank, its rotation had nowhere to go but faster. You have already watched this happen. A figure skater spins with arms stretched wide, then pulls them tight against her chest, and accelerates violently without pushing off anything. She added no energy of rotation. She only shrank her radius, and the ledger did the rest. The collapsing cloud did exactly the same thing on a scale beyond imagining, spinning up as it fell. But here is what most explanations skip past, and the omission matters enormously. Spinning faster does not flatten anything. A rapidly rotating cloud of gas will not, on its own, settle into a plate. Something else had to do the work, and that something was collisions. Picture the young cloud as an immense swarm of particles, each on its own path. Most of them share a broad common circulation, the direction the whole cloud was already turning. But every particle also carries some vertical motion, a component of travel above or below the average plane. Now watch what happens to each type of movement. The shared in-plane motion survives, reinforced constantly, because nearly every neighbor is doing the same thing. Traffic flowing the same way keeps flowing. The vertical motion has no such protection. A particle rising above the plane meets particles falling through it, and every collision between them cancels part of that up and down travel. Nothing replaces it. That energy converts into heat, radiates away into space as infrared light, and never returns. Astronomers call this collisional damping. Over millions of years, it drained the vertical dimension out of the entire cloud, particle by particle. Imagine throwing a handful of loose dry sand into a wide bowl spinning on a turntable. At first, the grains fly everywhere, some high, some low. But grains keep striking one another, each impact killing a little more of the up and down scatter, until what remains is a thin, even layer smeared across the bowl. Nobody flattened it. The collisions did. That layer became our solar system. Planets formed inside that thin sheet, assembled from material that already shared one orientation. They did not choose the plane. No other plane was available to them. Every grain, pebble, and boulder they grew from was already traveling in it. Look around today and the fingerprints remain everywhere. The asteroid belt hugs the plane. The organized inner portion of the Kuiper belt, the ring of icy debris beyond Neptune, clusters near it too. Every giant planet with rings holds those rings in a flat sheet around its own equator, because the same collisional physics runs at every scale, on every spinning system with material to grind down. Flatness is not decoration in this universe. Flatness is what rotation plus collisions inevitably produces. The most remarkable part of this story, we have been staring straight at the disk for thousands of years. Because we live inside a flat sheet, everything else in the sheet appears to us along a single narrow band across the sky. The sun tracks that band, the moon follows it. The planets wander back and forth along it and almost never leave it. Babylonian astronomers mapped that band and divided it into 12 equal parts in the late 5th century BCE, and their names for those segments still circulate in newspapers today. The zodiac. But strip the mythology away and the zodiac is something else entirely. The zodiac is the ecliptic projected onto the sky. What ancient sky watchers were tracking night after night for centuries was an edge-on view of the disk they were standing inside, the same way a person inside a vast flat room sees the far walls compressed into a single thin line. They built calendars on it, they timed the planting of crops by it, they navigated with it, and not one of them knew what they were looking at. Understanding arrived slowly. Through the 1500s and 1600s, as Copernicus and then Kepler moved the sun to the center, The near coplanar arrangement of the orbits became visible for the first time as a fact-demanding explanation. In 1755, Immanuel Kant proposed that a rotating cloud could collapse and flatten into a disk. In 1796, Pierre-Simon Laplace developed the idea in mathematical detail. Both men were essentially right. Neither could prove it. Proof took another 218 years. In November 2014, the Atacama Large Millimeter Array in Chile, 66 radio dishes spread across a high desert plateau, turned its full resolving power on a young star called H.L. Tauri, roughly 450 light-years from Earth. The light captured in that image left the star around the year 1564, the year Galileo Galilei was born, and had been travelling toward us ever since. What came back astonished everyone who saw it. A disk, flat, bright, and cut through with a series of dark, concentric gaps, like grooves in a record, almost certainly carved by planets forming inside it. Around a star barely 1,000,000 years old. For a moment, picture yourself out there, watching from a safe distance. You would see no scattered ball of material and no chaos. You would see a luminous plate of gas and dust wheeling slowly around a young star, thin as a coin against its own width, with dark rings where something is quietly sweeping its orbit clean. Our flatness turned out not to be a fluke. Our flatness is what happens, except the disk may not be as obedient as it looks, and two genuine disagreements sit unresolved at the heart of this. In 2017, Catherine Volk and Renu Malhotra at the University of Arizona measured the average orbital plane of distant Kuiper Belt objects, and found that between roughly 50 and 80 astronomical units from the Sun, that average plane appears to lean away from the invariable plane by around 8 degrees. 1 astronomical unit means the Earth-Sun distance, about 150 million kilometers, or 93 million miles. Their conclusion carried real weight. Something unseen may be tugging on that region. Their calculations suggested an undiscovered object, roughly the mass of Mars, orbiting near 60 astronomical units. But that result has been contested ever since. As more distant objects were catalogued, later analyses found the statistical significance of that particular warp fading. Then, in 2025, a new measurement published in the monthly notices of the Royal Astronomical Society reported a warp further out still, beyond 80 astronomical units, with the same suggestion attached, possibly the gravitational signature of an unseen planet. Nobody has settled it. The distant belt remains a place where the disker's discipline may quietly break down, and where our sample of objects is still too thin to be certain. The second disagreement is stranger, older, and closer to home. The Sun's rotation axis does not line up with the plane of its own planets. The misalignment measures about 6 degrees, 6 fingernails at arm's length. Astronomers first measured the Sun's rotation in the 1800s, and the tilt has been sitting there, unexplained, ever since. That should not happen. Star and disk form together out of the same rotating cloud, and their spins should match. Several explanations compete, and each one has supporters. In 2016, Elizabeth Bailey, Konstantin Batygin, and Michael Brown at Caltech argued that a distant, massive, inclined ninth planet could have slowly torqued the entire planetary plane over billions of years, producing exactly this misalignment. Others point to a primordial stellar companion that could have tilted the young disk, or to magnetic coupling between the newborn Sun and its disk, or to a passing star that disturbed the system early on. Recent surveys of other young stars found that roughly a third of isolated systems show similar misalignments from birth, suggesting the tilt may simply be an accident of formation rather than evidence of anything hidden. We do not know which answer is correct. The 6 degrees remain a genuine open question, a small, stubborn error in an otherwise beautifully organized machine. Set the arguments aside, though, and the essential picture holds. Our solar system is a disk of extraordinary rigidity, organized 4.6 billion years ago and holding its orientation ever since, with every large body inside it agreeing to within a few degrees, and a structure that flat gives the word up something it never had before. Not a sensation, not a local pull, a definition. Up for the solar system means perpendicular to the disk, straight out through the flat face of the plate, above it or below it, at right angles to the shared motion of everything we have ever known. That direction is not blocked. No wall stands there, no force forbids it. Space in that direction is as empty and as open as space in any other. Every ingredient for going there exists. So here is the thing that should be difficult to accept. In the entire history of spaceflight, out of every machine humanity has ever launched, almost nothing has ever gone that way. Not because we didn't think of it, because of a number. One specific speed, carried by every object born inside this disk, including the one you are standing on right now. 29.78 kilometers per second. That is how fast Earth moves around the Sun. 18.5 miles every second, over 66,000 miles an hour, close to 120 times faster than a passenger jet at cruising altitude. Take 3 seconds to absorb that sentence, and in those 3 seconds you personally travelled about 89 kilometers sideways through space, 55 miles, roughly the distance across a large city, covered while you sat perfectly still. You feel none of it. Nothing rattles, nothing rushes past, no wind, no sound. The motion is perfectly smooth because everything around you, the air, the ground, the building, the planet, moves with you at exactly the same speed. And that is precisely the problem. Every rocket ever launched from Earth begins its journey already travelling at 29.78 kilometers per second before its engines ignite. The rocket sits on the pad carrying it. The launch tower carries it. The people watching from a safe distance carry it. Clearing the atmosphere does not shed a single meter per second of that motion. A rocket climbing off the pad gains altitude, and altitude alone changes nothing about the sideways sprint it inherited. Think of standing on the deck of a ship moving at full speed and jumping straight up. You land in the same spot because you never stop moving with the ship. Rising doesn't cancel your travel. It only adds a small motion on top of a large one you never gave up. Here is where the story splits in two. For any mission travelling within the disk, to Mars, to Jupiter, to the outer solar system, that inherited speed is the single greatest asset a mission planner has. Nobody wastes it. Launch windows and launch directions get chosen specifically so the rocket's push adds to Earth's existing motion rather than fighting it. A spacecraft leaving Earth in the direction our planet already travels starts its interplanetary journey with a running start it never had to pay for. Voyager did this. New Horizons did this. Every outbound probe in history has done this. To understand how enormous that gift is, we need one number that governs all of it. At Earth's distance from the Sun, solar escape velocity measures about 42.1 kilometers per second, meaning an object moving that fast in any direction away from the Sun will never come back. It coasts outward forever, slowing but never stopping, permanently free of the Sun's grip. Earth already supplies almost 30 of those 42, which leaves roughly 12.3 kilometers per second for the engines to provide, a demanding but achievable figure, close to the speed a rocket already needs just to break free of Earth itself. Chemical rockets, paired with gravity assist from planets along the way, have paid that bill more than once. Escaping the entire solar system is expensive, but it is affordable. Now turn 90 degrees. Aim not outward through the disk, but straight up out of it, perpendicular to the plane, toward empty space above the flat face of the system. Everything reverses. That same inherited motion, the asset every outbound mission exploits, becomes the largest obstacle in spaceflight. Picture a playground merry-go-round spinning fast, and picture yourself standing near its outer edge, gripping the rail. Now, try to step off, not stumbling forward along the direction of spin, but cleanly outward, in a straight line away from the ride. You cannot. Your body carries the circular motion of the platform, and the moment you let go, you continue travelling sideways at the speed the ride gave you. To leave in any direction other than the one you're already going, you must first destroy the motion you already have. That is the entire problem, and it changes what going up actually means. Going up out of the solar system does not mean adding an upward push. Going up means erasing a sideways motion of 29.78 kilometers per second first, and only then building a new one in a completely different direction. Engineers measure this with a single number, delta V. Strip the term of its jargon, and it simply means the total change in velocity a spacecraft's engines must produce across an entire mission. Every burn, every course correction, every arrival and departure added together. Delta V works like a fuel budget written in units of speed. A mission gets one allowance, fixed at launch by how much propellant fits inside the vehicle, and every maneuver draws from the same account. Spend it, and no more arrives. So how much delta V does a 90-degree turn cost? The answer is brutally simple. Turning your path a full right angle costs roughly 1.4 times whatever speed you are already carrying. Run that against Earth's orbital motion, and the number lands at about 42 kilometers per second. Read those two figures side by side, and let the contradiction sit for a moment. Leaving the sun's gravity forever, permanently, from Earth's distance. 12.3 kilometers per second of engine work, turning 90 degrees while staying inside the solar system, around 42, over 3 times more expensive to change direction than to leave entirely. That should feel wrong, so let's be precise about why it happens. At low speeds, turning is cheap. Walking at a slow pace, you can pivot 90 degrees almost effortlessly. Now imagine sprinting at full speed and trying to change direction by a right angle without slowing down. Your legs cannot do it. The faster you travel, the more violently your existing motion resists redirection. At 29.78 kilometers per second, redirection becomes catastrophically expensive because the spacecraft must do 2 enormous jobs at once. Cancel one large motion, build another, both drawn from the same fuel budget, both paid in full. And here is the sentence that defines this entire story. No chemical rocket ever built or ever seriously proposed carries anything close to that propellant margin. Not the Saturn V, not the space shuttle, nothing on any drawing board. The direction is not blocked by physics. The direction is blocked by arithmetic. One workaround exists, and it is the reason anything ambitious has ever flown at all. A gravity assist, also called a slingshot. The mechanics are elegant and worth understanding properly, because most descriptions get them subtly wrong. A spacecraft approaching a planet accelerates as it falls inward, pulled by that planet's gravity. Then, climbing back out of the same gravitational well on the far side, it decelerates by exactly the same amount. Measured against the planet, the spacecraft arrives and departs at the same speed. Nothing gained. Measured against the sun, everything changes, because the planet itself is moving. As NASA's own mission documentation puts it, the spacecraft's path gets bent by the encounter, and the planet's orbital velocity gets folded into the spacecraft's sun relative motion, a component it does not lose on the way out. The approach geometry decides the outcome. Pass behind a planet in its orbit, and you borrow some of its momentum, leaving faster. Pass in front, and you surrender momentum instead, leaving slower. And that word, borrow, is not a metaphor here. The exchange is genuine, and the books balance exactly. Whatever momentum the spacecraft gains, the planet loses. NASA describes it plainly. The spacecraft tugs on the planet and actually reduces its orbital momentum by a tiny amount. Imagine a gnat colliding with a freight train. The train's speed change is real and utterly unmeasurable. The gnat's is dramatic. Gravity assists are not free energy. Gravity assists are alone taken out against a planet's orbital motion in an amount so small the lender will never notice. Everything so far follows one underlying law, and once you see it, the entire solar system starts making sense. The cost of changing an orbital plane scales directly with the speed you already carry. Fast motion, expensive turn. Slow motion, cheap turn. Watch it play out at 3 different scales. Stand on the equator and Earth's rotation carries you eastward at 0.465 kilometers per second, about 1,674 kilometers per hour, or 1,040 miles per hour, faster than sound, which travels at roughly 1,235 kilometers per hour at sea level. You are being carried through the air at about 1 1/3 times the speed of a sonic boom, and you have never once noticed. But compared to Earth's motion around the Sun, that spin is trivial, about 1/64th as fast. A satellite in low Earth orbit travels at roughly 7.8 kilometers per second, substantial and still only about a quarter of our planet's solar orbital speed, which is exactly why polar orbits are routine. Weather satellites, Earth imaging fleets and reconnaissance spacecraft fly over the poles every single day, crossing the equator at right angles to it. Nothing exotic about them. They launch that way from the start, and at these speeds, planning a steeply inclined orbit costs a manageable amount of extra performance rather than an impossible one. The payoff is elegant. A satellite on a polar path circles the planet north to south while Earth rotates beneath it, so each pass sweeps a fresh strip of surface. Picture peeling an orange in one continuous ribbon. The peeler stays in place while the fruit turns. Over roughly a day, the whole globe passes underneath. Even the compromises here are political rather than physical. The International Space Station flies at an inclination of 51.6 degrees, an unusual, seemingly arbitrary number that exists because Russia's primary launch site at Baikonur sits at about 46 degrees north, and launching into an orbit tilted less than your own latitude wastes enormous energy. 51.6 degrees was the negotiated figure, steep enough for Russian rockets, shallow enough for American launches from Florida. At Earth scale, we argue about geography. At solar scale, the argument ends before it starts. The same law explains something you have seen in the sky since childhood, without knowing what caused it. The Moon's orbit tilts about 5.145 degrees from the plane of Earth's orbit, a small angle, roughly 5 fingernails held at arm's length against the sky. That tiny tilt is why we do not have an eclipse every month. The Moon reaches new phase, positioned between us and the Sun, roughly every 29.5 days. If the Moon orbited exactly in Earth's orbital plane, every one of those alignments would produce a solar eclipse, and every full moon would produce a lunar one, more than 20 eclipses a year. Instead, the Moon usually passes slightly above the Sun or slightly below it, and its shadow misses Earth entirely. Eclipses require the Moon to be new or full and to be crossing the plane at the same moment. Astronomers call those crossing points the nodes, the two places where the tilted lunar orbit intersects Earth's orbital plane, like the 2 points where a slightly tipped hoop passes through a flat sheet. Line up the phase and the node together, and the shadow lands. Miss by a little, and nothing happens. That is why eclipses arrive in clusters roughly twice a year, in what astronomers call eclipse seasons, the windows when the geometry briefly permits it. 5 degrees. That is the entire difference between an eclipse being a monthly routine and a rare event people cross continents to witness. Now, the most striking demonstration of all. Saturn's rings do not lie in the plane of Saturn's orbit around the Sun. The rings sit in the planet's own equatorial plane, tilted about 26.73 degrees to its orbital path, because the same physics that flattens any spinning colliding system aligned them with Saturn's spin, not with its journey. So as Saturn moves along its 29.5-year orbit, our viewing angle shifts. Sometimes we look down on the rings from above, wide open and spectacular. Sometimes we drift into their exact plane. And when that happens, the rings vanish. Not fade, vanish, almost entirely, from a system hundreds of thousands of kilometers across. The last crossing occurred on the 23rd of March, 2025. The next will not arrive until October 2038. The reason lies in a proportion that barely feels real. Saturn's main rings span about 273,600 kilometers, roughly 170,000 miles, nearly 3/4 of the distance from Earth to the Moon, and in most places they measure only around 10 meters thick, 30 feet, shorter than the height of a 3-story building. Try to hold both numbers at once. Take an ordinary sheet of paper about 1/10 of a millimeter thick. To match the proportions of Saturn's rings, that sheet would need to be about 2.7 kilometers wide, around 1.7 miles, a single page of paper stretching across an entire town. If you could safely position yourself exactly in that plane and look along it, one of the most recognizable structures in the solar system would narrow to a thread of light, and then, essentially, stop existing. Earth's spin, the Moon's orbit, Saturn's rings, the Sun's disk, every one of them flat, every one of them aligned by the same combination of rotation and collision, and every one of them charging the same toll to anything trying to leave. Flatness is never an accident in this universe. Something forced it, and once forced, leaving costs in exact proportion to the speed the structure carries. At Earth's surface, that toll is small enough to ignore. In low orbit, small enough to pay routinely. At the Moon's distance, small enough that a 5-degree difference merely rearranges our eclipse calendar. At solar scale, the toll rises to 42 kilometers per second, a bill no engine humanity has built or drawn or seriously imagined can settle, which leaves one question standing, and it is not rhetorical, because in 1990, one spacecraft went there anyway. Its name was Ulysses. One spacecraft in the entire history of spaceflight, designed from the first sketch to do the one thing the arithmetic forbids, to leave the plane of the solar system deliberately and look down on it from above, not as a side effect, not as leftover geometry from some other objective, as the mission, a joint project between the European Space Agency and NASA, originally conceived in the 1970s under the name the International Solar Polar Mission. The idea was old and obvious, and for decades, completely impossible. Nobody had ever seen the sun's poles. Every telescope on Earth, every solar observatory ever launched, every photograph ever taken of our own star had been captured from within the disk, meaning always from the side, always looking at the sun's equator, never once from overhead. We had studied the sun for 4 centuries and had never seen the top of it. On the 6th of October, 1990, Ulysses lifted off inside the cargo bay of Space Shuttle Discovery. Once in orbit, the crew released it, and 2 solid fuel upper stages, an inertial upper stage followed by a payload assist module, fired in sequence to hurl it away from Earth. Departure speed was around 15 kilometers per second, roughly 9 1/3 miles every second. At that moment, Ulysses became the fastest object humanity had ever launched, a record it held until New Horizons left for Pluto 16 years later. Its mission was to survey the heliosphere, the enormous bubble of charged particles and magnetic field that the sun blows outward around itself, the invisible territory our entire solar system sits inside, at every solar latitude, equator to pole, top to bottom, and to do that, its engineers ran straight into the wall. No rocket then existing, and none since, could cancel enough of Earth's orbital motion to tip a spacecraft over the sun's poles directly. The European Space Agency stated the problem plainly in its own mission documentation. So much energy is needed that even with today's most powerful launch vehicles, direct injection cannot be achieved. So the solution was not power. The solution was patience, and 2 physical advantages stacked one on top of the other. The first advantage, turning is cheapest where you move slowest. Out at Jupiter's distance from the Sun, a spacecraft coasts along at about 13 kilometers per second, under half the pace of Earth's own orbital sprint. The same 90-degree turn that costs an impossible fortune near Earth becomes dramatically cheaper out there, simply because there is less motion to fight. The second advantage, Jupiter itself. No engine ever built can bend a trajectory the way a planet 318 times the mass of Earth can. So the plan inverted itself completely. To go up, Ulysses first went out. For 16 months it coasted outward through the disk. Then, at 2 minutes past noon, Universal Time on the 8th of February 1992, Ulysses passed within 378,400 kilometers of Jupiter, about 235,000 miles. Hold that distance for a second, because it happens to be almost exactly the distance from Earth to the Moon. Now picture yourself aboard at that moment. Jupiter fills a vast swath of your view, banded in cream and rust, storms wider than our entire planet turning slowly beneath you. You are not orbiting, you are falling past, and the giant is quietly rotating your entire path through space as you go. Deliberately, engineers kept the spacecraft well away from Jupiter's inner radiation belts, where the particle environment would have destroyed the instruments. That constraint set a ceiling on how far the trajectory could be bent. Even so, the encounter rotated Ulysses' orbital plane by roughly 80 degrees. Think about what just happened. No engine fired, no propellant burned. A single unpowered pass, and a spacecraft that had spent its whole life inside the plane of the solar system was now traveling almost perpendicular to it. The resulting orbit swung from about 1.3 astronomical units from the Sun at its closest to 5.4 at its farthest, from just outside Earth's orbit to just past Jupiter's, taking 6.2 years to complete one lap, roughly the time between one Olympic Games and the next, and a half. The first southern polar pass began in late June 1994, and in September of that year, Ulysses climbed to a maximum solar latitude of 80.2 degrees, not quite directly overhead, but closer than anything before or since. The northern pass followed in mid-1995. Across its prime mission, the spacecraft spent 234 days above 70 degrees of solar latitude, roughly 8 months of continuous observation from a vantage point no human instrument had ever occupied. What it found rewrote the picture of our star's atmosphere. The solar wind, the constant stream of charged particles the sun exhales in every direction, turned out not to be uniform at all. From the cooler polar regions, where the magnetic field opens directly into space through structures called coronal holes, Ulysses measured a fast, remarkably steady wind blowing at about 750 kilometers per second. That figure needs translating. At that speed, a particle leaving the sun's pole would cross the entire distance from Earth to the Moon in about 8.5 minutes, less time than it takes to boil an egg. Meanwhile, the slow and medium-speed wind, around 350 kilometers per second, less than half as fast, proved confined to a narrow band hugging the solar equator. Two completely different winds, one star. Nobody had known. The heliospheric magnetic field also turned out to be considerably more complex than pre-mission models had predicted, and Ulysses detected interstellar dust drifting into our solar system from the galaxy beyond, along with direct measurements of interstellar gas, material that had never belonged to the Sun at all. The spacecraft kept working for more than 18 years, completing 3 full orbits and passing over both solar poles 3 times each, before controllers finally shut it down on the 30th of June, 2009. Here is what makes the story land differently than it first appears. Ulysses did not break the barrier. Ulysses confirmed it. The spacecraft never paid the plane change bill. Not 1 kilometer per second of it came from its own engines. Every scrap of that 80-degree rotation came from Jupiter. Momentum quietly subtracted from the largest planet in the solar system and handed to a machine weighing 371 kilograms, about 818 pounds, roughly the weight of a grand piano. The only object that ever climbed did so by borrowing. And the moment you understand that, every other spacecraft's angle starts to look different too. 5 spacecraft are currently leaving the solar system entirely: Voyager 1 and 2, Pioneer 10 and 11, and New Horizons. 2 of them are traveling at steep angles to the disk, and neither one meant to. Voyager 1 is climbing above the plane at about 35 degrees, moving roughly 520 million kilometers a year, around 320 million miles. That angle exists because of one decision made in 1980. Mission planners aimed Voyager 1 closely past Titan, Saturn's largest moon, to investigate its thick atmosphere. The trajectory required to do that took the spacecraft beneath Saturn's south pole, and the encounter bent its path permanently northward, out of the plane. The cost was enormous. That choice ended Voyager 1's planetary tour on the spot. Uranus and Neptune, two entire worlds, were traded for one close look at a single moon. The spacecraft's small thrusters could adjust its orientation, but nothing aboard could undo a turn of that magnitude. Voyager 2, launched on the trajectory that preserved the outward option, went on to visit both ice giants instead. And now, for a detail, most accounts get backwards. People often assume Voyager 1, the famous one, the record holder, is the steeply angled spacecraft. Voyager 2 is diving below the ecliptic at about 48 degrees, heading toward the constellations Sagittarius and Pavo, 13 degrees steeper than its twin. Neither angle was ever a design goal. Both are simply residue, the geometric leftovers of planetary encounters that happen to bend each craft's path and leave it there forever. Even our most celebrated departures from the plane were accidents, which brings us to the mission climbing right now, using the opposite philosophy. Solar Orbiter, another joint effort between the European Space Agency and NASA, launched on the 10th of February 2020. Rather than one dramatic Jupiter encounter, it takes the slow road, repeated flybys of Venus, each one nudging its orbit a little further out of the plane. Engineers describe it as a stairway rather than a leap. Following a close Venus flyby in February 2025, Solar Orbiter reached an inclination of 17 degrees relative to the Sun's equator. 17 degrees does not sound like much, but 17 degrees was enough. On the 16th and 17th of March, 2025, from a viewing angle of about 15 degrees below the solar equator, three of its instruments, the polarimetric and helioseismic imager, the extreme ultraviolet imager, and the spectral imaging of the coronal environment, captured the first images ever taken of the Sun's south pole. Sami Solanki of the Max Planck Institute for Solar System Research, who leads the imaging instrument team, described the poles as literally unknown territory. Nobody knew exactly what the pictures would show. Early results revealed the polar magnetic field in a complex, mixed, turbulent state, captured by good fortune right as the Sun approaches the peak of its 11-year cycle, when its magnetic polarity flips. The climb continues. A Venus flyby scheduled for Christmas Eve 2026 should raise the tilt to 24 degrees. By 2029, around 33 degrees. Ulysses carried no cameras at all, only instruments to taste particles and measure fields. It flew over the Sun's poles 4 separate times and never photographed them. Solar Orbiter is finally filling that gap, one Venus encounter at a time. One more mission demonstrates the principle from the opposite direction, and it may be the clearest proof of all. Parker Solar Probe, launched in August 2018, had to reach the Sun. Most people assume falling inward toward a star is easy. Gravity does the work, surely. But the same inherited sideways motion that makes climbing impossible also makes falling impossible. A spacecraft leaving Earth carries so much orbital velocity that it simply circles the Sun rather than approaching it. To fall inward, Parker had to shed speed, a great deal of it. The solution was identical in kind to Ulysses. 7 Venus flybys across roughly 6 years, each one trimming a little velocity and tightening the orbit, until the last one on the 6th of November 2024 set up the final approach. On the 24th of December 2024, Parker Solar Probe passed 6.1 million kilometers above the Sun's surface, about 3.8 million miles, traveling at 692,000 kilometers per hour, 430,000 miles an hour, or about 192 kilometers every second. At that pace, the spacecraft could cross from Washington to Tokyo in under a minute, fastest object humanity has ever made, and it got there by giving speed away, not by adding it. 2 missions, opposite destinations, identical lesson. Extreme places in this solar system are not reached with engines. They are reached by borrowing momentum from planets and by waiting. One technology keeps appearing in every serious answer to this problem. Ion propulsion works nothing like a rocket. Instead of burning fuel violently, an ion engine strips electrons from atoms of xenon gas and accelerates the charged remnants out the back using electric fields. The exhaust glows faint blue. The thrust is almost comically small. The German Aerospace Center described the sensation precisely. The push equals about the pressure of a sheet of paper resting on your outstretched palm. But it never stops. And over years of continuous operation, tiny becomes enormous. NASA's Dawn spacecraft, which orbited both Vesta and Ceres in the asteroid belt, accumulated more than 11 kilometers per second of velocity change from its ion engines alone, the largest amount of onboard propulsion any spacecraft has ever generated under its own power. 11 kilometers per second. Remarkable, record-setting, and still nowhere near the roughly 42 required to turn a right angle at Earth's orbital speed. Whether low-thrust electric propulsion could ever deliver a plane change of that magnitude remains genuinely untested. Supporters point to the accumulating evidence that patience beats power. Skeptics note that no mission has ever attempted anything close, and that the trip times involved may exceed what any funded program would tolerate. Several successors have been designed on paper. Solaris, selected for early study under NASA's MIDEX program, would take the Ulysses route, out to Jupiter, slingshot upward, but carrying the cameras Ulysses lacked, reaching above 75 degrees of solar latitude to finally image the poles properly. Polaris and the high inclination. Solar mission proposed something bolder. Solar sails. Enormous mirror-thin sheets pushed by nothing but the pressure of sunlight itself, spiraling a spacecraft into a circular orbit at 0.48 astronomical units, about half Earth's distance from the Sun, tilted 75 degrees out of the plane. But sail readiness is disputed, and honestly so. The concepts require sails vastly larger than anything ever flown. NASA's own demonstrator, Solar Cruiser, designed with a sail of about 1,650 square meters, roughly the area of 6 tennis courts, was cancelled in 2022 after review found the project could not meet its schedule and budget. The technology has never been tested at the scale these missions assume. Supporters argue that steady progress from smaller sails will close that gap. Critics point out that a cancelled demonstrator proves nothing except difficulty. For now, every credible plan still ends with the same 3 words. Borrow from Jupiter. Ulysses went. Solar Orbiter is going. The direction is not sealed, which finally raises the question this entire story has been circling toward. The one nobody asks because almost nothing has ever travelled far enough to answer it. If you did climb out of the plane, what would actually be there? The direction has an address. 2 of them, actually. Stand outside on a clear night in the northern hemisphere and look toward Draco, the long, winding dragon that curls around the Little Dipper. Somewhere in the dragon's eastern coil, between the stars Delta and Zeta Draconis, sits an unmarked point in the sky called the North Ecliptic Pole. That point is straight up, not up from where you're standing, up from the entire solar system. A line drawn from the Sun, perpendicular to the plane of the planets, passes through that spot in Draco and continues forever. Directly opposite, on the other side of the sky, lies the South Ecliptic Pole, in the southern constellation Dorado, not far from the large Magellanic Cloud, invisible to most of the northern world. 2 points, one above, one below, and in 4.5 billion years of solar system history, almost nothing has ever travelled toward either of them. Consider what a spacecraft aimed at one of those points would experience. It would climb away from the asteroid belt, away from the Kuiper belt, away from the fine haze of interplanetary dust that fills the plane. Within a relatively short distance, every familiar structure of the solar system would fall beneath it, and then it would gain something no human instrument has ever had. An overhead view. Imagine watching a record spinning on a turntable, but from directly above rather than from the side. Every groove visible at once, the whole rotation laid out flat beneath you. the inner planets racing through their tight, fast circles, Jupiter and Saturn wheeling slowly around the outside, the belt as a thin, bright ring between them. We have never seen that. Not once. Every photograph, every diagram, every map of our solar system's layout has been reconstructed mathematically from measurements taken inside the disk, the way you might map the floor plan of a building you can only ever crawl through. Ulysses came closest. It reached a little over 80 degrees of solar latitude, near the top, but not the top, 10 degrees short of directly overhead, on a trajectory that was itself borrowed. Nothing has ever stood at 90. Now, before that sounds like pure neglect, consider what a mission planner gives up by going there. The reluctance is not stubbornness. The reluctance is arithmetic of a different kind. Nearly everything worth visiting sits in the plane. The asteroid belt, hundreds of thousands of catalogued bodies, lies within a few degrees of it. Jupiter's Trojans, two enormous swarms of asteroids, locked into gravitationally stable pockets, 60 degrees ahead of and 60 degrees behind the planet, share Jupiter's orbit and Jupiter's plane. Short-period comets, the ones that return on human timescales, come from the Kuiper belt and cluster close to the ecliptic too. A mission that climbs out of the disk trades all of it. Every free flyby, every opportunistic target, every bonus science observation on the way to somewhere else, surrendered in exchange for a region that is, by definition, almost completely empty. That is the honest reason so little has gone up. Not just the fuel, the emptiness waiting at the end of the fuel. But here is where the story turns. The disker's authority is not uniform. Push outward far enough and the flatness begins to fail. Look at the inner solar system first. Mercury tilts about 7 degrees, the largest inclination among the 8 planets, and almost certainly a fossil of the violent, collision-heavy environment where it formed close to the Sun, in a crowded region where bodies smashed into each other constantly. Jupiter and Saturn sit among the flattest of all, assembled from the calmest, most settled part of the disk. Then comes Pluto, and the pattern breaks. Pluto's orbit tilts 17.16 degrees to the ecliptic, more than double Mercury's, more than 13 times Jupiter's. That tilt is not original. Pluto almost certainly did not form there. Its orbit carries the signature of disruption involving Neptune, back when the giant planets were still migrating through the young solar system, shoving smaller bodies out of the plane as they moved. And once you pass Neptune, the tilts get genuinely strange. Eris, discovered in 2005 by Mike Brown, Chad Trujillo, and David Rabinowitz, the object whose discovery ultimately cost Pluto its planetary status, orbits at roughly 44 degrees to the ecliptic. 44 degrees is not a tilt. 44 degrees is a rebellion. Picture a dinner plate again, and now picture one object cutting through it at nearly the angle of a staircase, spending most of its 557-year orbit high above or far below everything else in the system. Then there is Sedna, and Sedna requires more care. Its inclination measures just under 12 degrees, which sounds almost modest until you account for where Sedna goes. Its closest approach to the Sun sits at about 76 astronomical units, with 1 astronomical unit meaning the Earth-Sun distance, roughly 150 million kilometers or 93 million miles. Its farthest point reaches around 937. At those distances, a small angle becomes an enormous displacement. 12 degrees applied at 500 astronomical units lifts an object roughly 100 astronomical units clear of the plane, more than 3 times Neptune's entire distance from the Sun, measured straight up. Sedna takes about 11,400 years to complete one orbit. The last time it was where it is now, the last ice age had only just released its grip on Earth, and the first human beings anywhere were beginning to plant crops instead of chasing them. And then there is the object that made astronomers genuinely uncomfortable. Catalogued as 2015 BP 519, discovered by the Dark Energy Survey in Chile, it has a semi-major axis of about 428 astronomical units, a perihelion well beyond Neptune's reach, and an inclination of 54 degrees. 54 degrees. An object born presumably in a flat disk, now travelling on a path more than halfway to perpendicular. A collapsing cloud that flattens itself through collisions does not produce that. Something else did. In 2016, Konstantin Batygin and Michael Brown at Caltech proposed an answer that has dominated the conversation ever since. Planet 9. Their argument was statistical rather than visual. The most distant Kuiper belt objects, they showed, do not point in random directions. Their orbits appear to cluster, reaching their closest approach to the Sun in roughly the same region of sky, and sharing roughly the same tilted orbital plane. A distant, massive, inclined planet, they argued, would shepherd exactly that pattern into existence over billions of years. Crucially, the model made a prediction. Such a planet should also generate a population of objects thrown onto steeply inclined orbits. Objects like 2015 BP 519. Jessica Becker, who found that object as a graduate student, ran simulations with and without a ninth planet. With Planet 9 included, the object's bizarre orbit reproduced itself naturally. But the case has never closed, and the objection is a serious one. Critics argue that the clustering may be an illusion created by where we happen to have looked. Telescopes do not survey the sky evenly. They point at particular patches, during particular seasons, under particular conditions, and a biased search naturally produces what looks like a biased result. If astronomers only ever examined one region of sky, everything they found would appear to cluster there. Brown and Batygin took that criticism seriously and attempted to quantify it. Their bias-corrected analysis, published in 2019, put the odds of the observed clustering arising by chance at about 0.2%, roughly 1 in 500. Still contested, and the evidence has kept complicating. In 2025, astronomers using the Subaru telescope in Hawaii announced a new object, 2023 KQ-14, nicknamed Ammonite, only the fourth known sednoid, a body so distant that even at its closest approach it never feels Neptune's pull. Its orbit points the wrong way. Where the three previously known sednoids cluster in one direction, Ammonite's points nearly opposite. Yukun Huang of the National Astronomical Observatory of Japan put it plainly. The fact that Ammonite's orbit does not align with the others lowers the likelihood of the Planet 9 hypothesis. He offered an alternative worth sitting with, that a planet may indeed have existed out there once, sculpted these orbits, and was then ejected from the solar system entirely, leaving only its fingerprints behind. The debate remains genuinely, uncomfortably open. What changes this is not argument. What changes this is data. On the 30th of June, 2026, barely a month ago, the Vera C. Rubin Observatory in Chile officially began the Legacy Survey of Space and Time, a 10-year campaign to photograph the entire southern sky every few nights with the largest digital camera ever built. During its early optimization runs alone, before the survey formally started, Rubin discovered over 11,000 previously unknown asteroids in about 6 weeks, including 380 trans-Neptunian objects, 11,000 new bodies in 6 weeks. For comparison, humanity catalogued its first 11,000 asteroids over the course of roughly a century and a half. Michael Brown himself has said he is most interested to see whether Rubin finds Planet 9. Within a few years, the survey should either produce the planet or produce enough unbiased objects to demonstrate that the clustering was never real. Either outcome resolves it. Neither outcome is guaranteed to be the one anyone expects. Push further out, much further, and the disk question changes shape entirely. Beyond the Kuiper belt lies the Oort cloud, the most distant material still gravitationally bound to the Sun, occupying a region running from roughly 1,000 to 100,000 astronomical units. That outer figure deserves a moment. 100,000 astronomical units equals about 1.5 light years. The nearest star system to us sits 4.2 light years away, which means the Sun's outermost possessions may reach more than a third of the way to Proxima Centauri, and nobody has ever seen a single object in it. Not one. The Oort cloud's existence rests entirely on inference, specifically on the trajectories of long-period comets, the ones that swing through the inner solar system on orbits, taking thousands or millions of years. Here is the observation that built the theory. Short-period comets from the Kuiper belt arrive along the plane, as you would expect from a flat source. Long-period comets do not. They arrive from every direction at once, above, below, sideways, at every conceivable angle. That randomness is the evidence. A spherical shell, with no preferred plane at all, would produce exactly that pattern. So astronomers concluded the Oort cloud must be spherical. For decades, that picture stood unchallenged. In February 2025, David Nesvorny of the Southwest Research Institute and colleagues published a modeling study using NASA supercomputers and found something nobody expected. The inner Oort cloud, according to their simulations, is not a shell. The inner Oort cloud is a warped disk with a spiral structure, two arms curving outward, spanning roughly 15,000 astronomical units in length, and tilted about 30 degrees to the ecliptic. Seen from a distance, our solar system's outermost inhabited region would look less like a bubble and more like a tiny galaxy. What sculpts it is not the Sun. Out there, the Sun's grip has grown so weak that a different force takes over: the galactic tide, the combined gravitational pull of the entire Milky Way, acting differentially across the region. Objects scattered out to those distances slowly have their orbital planes rotated by that pull over hundreds of millions of years until they settle into the spiral, and the structure lasts. The researchers found it forms within the first few 100 million years after the solar system's birth and persists to the present day, stable across billions of years, appearing in every simulation regardless of which passing stars were included. Now, for the honest part. Confirming it observationally may be effectively impossible with current instruments. The paper's own authors describe the prospects for detection as feeble. The objects are impossibly faint, impossibly far, and no resources have been committed to the search, so the disagreement stands unresolved. The traditional spherical model still explains the comet data adequately. The spiral model explains the same data and predicts additional structure we may not be able to check for decades. But sit with the implication for a moment, because it is quietly staggering. If the modelling holds, then even the outermost boundary of our solar system carries a plane, not inherited from the Sun, inherited from the galaxy. One more category of object drives the point home, and these we can actually see. 3 visitors have now arrived from outside the solar system entirely. Objects on paths so fast and so open that the Sun can never hold them. The first, in 2017, 1. I/Oumuamua, arriving at an inclination of about 123 degrees. Past 90 degrees, an orbit runs backward relative to the planets, so Oumuamua came through tilted steeply and travelling against the grain. The second, in 2019, 2 I/Borisov, at about 44 degrees. The third, discovered on the 1st of July, 2025, 3 I/Atlas, at 175 degrees, almost exactly retrograde, sweeping through our plane in the opposite direction to every planet in it, at roughly 60 kilometers per second relative to the Sun. None of them cared about our disk. None of them paid anything to cross it at those angles. They arrived carrying momentum from wherever they were born, on trajectories that we, with our chemical rockets and our borrowed gravity assists and our decade-long Venus stairways, cannot afford. That is the strange asymmetry at the heart of this. The universe sends objects through our plane at every angle imaginable, constantly, for free. We cannot leave it at any angle at all without begging a planet for help, which brings the whole question into a shape it has been quietly taking for some time. The spiral in the outer dark is not oriented by our Sun. It is oriented by the Milky Way, tilted 30 degrees away from the plane we live in, twisted into position by a gravitational tide from a structure so much larger than our solar system that our entire solar system is a rounding error inside it. Our disk is not the only disk. Our disk sits inside another one, vastly bigger, vastly older, formed by the same physics on a scale that dwarfs everything we have discussed. And that larger disk has its own perpendicular, its own definition of straight up, tilted steeply against ours. The Milky Way is a disk, not a cloud of stars, not a swarm, not a sphere. A flattened, rotating plate of several 100 billion stars, gas and dust, built by exactly the same physics that flattened our solar system, running on a scale so much larger that comparison almost fails. A vast cloud collapsed, rotation concentrated as it shrank. Collisions between gas clouds cancelled the up and down motion, converting it to heat that radiated away, until what remained was a thin, spinning sheet. Same story, same mechanism, different by a factor of billions, and our entire solar system, every planet, every comet, the Oort cloud, all of it, sits embedded inside that larger sheet like a single grain of sand pressed into a dinner plate the size of a continent. Our Sun occupies a position in a structure called the Orion Arm, a minor spiral feature, roughly 26,000 light-years from the galactic center. That number is worth slowing down for. Light leaving the galactic center right now will not arrive here for 26,000 years, and the light reaching your eyes tonight from that direction departed when Earth was still deep in the last ice age, when humans were painting animals on cave walls in Europe and mammoths still walked across the northern continents. That is one trip across our own galaxy, at the fastest speed the universe permits. Now, here is the part you have already seen with your own eyes without recognizing it. Look up on a genuinely dark night, far from city light, and a pale band arcs across the sky, faint, milky, slightly grainy, running from horizon to horizon. That band is not a cloud. That band is the galaxy, seen edge-on from inside. We live within a flat structure, so when we look along the plane of that structure, we see billions of stars stacked one behind another and blurred into a single luminous stripe. Look perpendicular to it, and the stars thin out dramatically, because in that direction the disk simply ends. The exact same situation produced the zodiac. Two flat structures, two edge-on views, two bands across the sky, one made of planets, one made of stars, both of them nothing more than the signature of living inside something flat. Now put the two together, and something strange emerges. Our solar system's plane is tilted about 60 degrees to the plane of the Milky Way. 60 degrees is not a minor misalignment. Lay a book flat on a table to represent the galaxy, then stand a second book against it at a steep angle, closer to upright than to flat. That is our relationship to the galaxy we live in. We are not lying neatly within the galactic disk. We are canted across it, and nobody should expect otherwise because the two orientations have nothing to do with each other. The Milky Way's plane was set by the collapse of an enormous mass of primordial gas, billions of years before our Sun existed. Our solar system's plane was set 4.5 billion years ago by one small local cloud that happened to be rotating in its own arbitrary direction when it began to fall inward. Two entirely separate formation histories. Two entirely separate answers to the question, which way is up? Neither one knows the other exists. The Sun does not sit still inside the galaxy. It orbits, and one complete circuit takes somewhere between 225 and 250 million years. Try to place that. The last time the Sun completed a full lap and returned to roughly this position, the largest mass extinction in Earth's history had only recently finished clearing the planet, and the first dinosaurs had not yet appeared. Every dinosaur that ever lived, every bird descended from them, every mammal, every human being, every civilization. All of it fits inside a single galactic year with room left over. You have completed a vanishingly small fraction of one lap in your lifetime, perhaps a 10 millionth. But the orbit is not the interesting part. Layered on top of that circular journey is a second motion, and this one matters far more to the story. The sun does not travel around the galaxy in a perfectly flat circle. The sun bobs, rising above the galactic plane, slowing, falling back through it, dropping below, slowing again, and returning. The mechanism is straightforward once you see it. All the mass of the galactic disk, stars, gas, dust, and whatever unseen material accompanies them, is concentrated near the midplane. Drift above that plane, and the combined gravity of everything below pulls you back down. Overshoot, and the same pull acts in reverse. Think of a weight on a spring, or a swimmer floating up and sinking back toward a dense layer of water. The disk's own gravity acts as a slow restoring force, and the sun oscillates through it again and again for the entire life of the solar system. That much, astronomers agree on completely. How fast it happens, they do not. The disagreement here is real, and it has persisted for 40 years. Early work in the 1980s calculated half periods, the time from one crossing of the plane to the next, ranging from 26 to 37 million years, with maximum heights above the plane between 49 and 93 parsecs. Later work, using data from the Hipparcos satellite, pushed the crossing interval toward roughly 42 million years. Then, in 2005, Douglas Gies and John Helsel derived a full oscillation period near 63.6 million years, a figure that other researchers have since built entire hypotheses around. Other models run past 70 million. Why such a wide spread? The original 1985 analysis named the culprit directly, and the answer has barely changed since. The largest uncertainty comes from the unknown distribution of the unseen mass that must be present to explain how the observed stars actually move. We cannot time the bob, precisely because we cannot see everything doing the pulling. What most estimates do agree on is the amplitude, around 70 parsecs, roughly 230 light-years above and below the midplane at the extremes. And that sounds enormous until you learn the disk's own thickness. Recent measurements using data from the Gaia spacecraft put the thin disk's scale height at around 260 parsecs, which means the sun never actually leaves. We bob near the surface of a much deeper layer, like a swimmer rising and sinking within the top few feet of a deep pool, never breaking through. Right now, we sit close to the midplane, drifting slowly northward, and here the story becomes genuinely contentious because those crossing intervals landed uncomfortably close to another set of numbers. In 1984, David Raup and Jack Sepkoski published evidence for a roughly 26 million year periodicity in marine mass extinctions across the fossil record. Within months, other researchers noticed the resemblance to the sun's galactic bobbing and proposed a connection. The reasoning was plausible. Passing through the dense midplane might gravitationally disturb the Oort cloud, sending comet showers inward, or the changing shielding from galactic magnetic fields might modulate the cosmic ray flux reaching Earth's atmosphere. Supporters have kept the idea alive with fresh analyses. Studies of well-dated impact craters have reported cycles in the range of 26 to 36 million years, and some researchers argue a stable cycle near 27 million years extends back through the last 540 million years of the fossil record. But the objections are serious, and they come from careful work. Corinne Baylor-Jones at the Max Planck Institute for Astronomy ran a full Bayesian analysis of the terrestrial impact cratering record in 2011 and found no convincing evidence for periodicity at all. His broader review concluded there is little evidence for intrinsic periodicities in biodiversity, cratering, or climate on these timescales. Others have shown something sharper still. Some apparent periodicities in the crater record appear to be artifacts of how geologists round their dates, a human signal masquerading as a cosmic one, and one plain observation cuts through the statistics. The Sun crossed the galactic midplane in the geologically recent past. No corresponding mass extinction followed. The honest position, the vertical motion, is well established. Its consequences for life on Earth are not. Two things can be true at once: a real motion and a correlation that may never have existed. The Milky Way is not alone either. Our galaxy belongs to the Local Group, a small gravitationally bound collection dominated by ourselves and the Andromeda Galaxy, accompanied by dozens of much smaller dwarf galaxies. And in 2014, R. Brent Tully at the University of Hawaii and his colleagues published something that redrew the map entirely. Rather than measuring where galaxies sit, they measured how galaxies move, tracing the flow patterns of thousands of galaxies to find where the streams converge. What they found, and named Laniakea, Hawaiian for immense heaven, contains roughly 100,000 large galaxies and spans over 500 million light-years. Our entire Local Group sits near its outskirts, drifting inward with everything else. Beyond Laniakea lies the cosmic web, filaments of galaxies strung like beads along invisible threads, dense knots where filaments intersect, and between them, voids, colossal, nearly empty regions where almost nothing exists at all. And here, finally, something changes. At this scale, no rotating structure dominates anything. The cosmic web does not spin. Filaments do not orbit. Nothing at that magnitude has collapsed, spun up and flattened, because the universe has not existed long enough for structures that large to complete even a fraction of a rotation. Which means, for the first time in this entire story, no plane exists to be perpendicular to. Astronomers call the governing assumption isotropy, the idea that the universe looks statistically identical in every direction. Not identical in detail, but identical in its overall properties. No special axis, no preferred direction, no cosmic up. The strongest evidence comes from the oldest light in existence. The cosmic microwave background, released roughly 380,000 years after the beginning, when the universe first cooled enough for light to travel freely, arrives from every direction in the sky. And once you subtract the effect of our own motion, that light varies in temperature by only about 1 part in 100,000 across the entire sky. Try to feel that precision. Take a person 1.7 meters tall, around 5'7", and measure a variation of about 17 microns, roughly a quarter the width of a single human hair. That is how uniform the universe looks at its largest scale, which is precisely why any deviation matters enormously. One deviation we already understand. The microwave background is slightly hotter in one direction and slightly cooler in the opposite, a simple Doppler effect, caused by our own movement. From that pattern, the Planck spacecraft measured our velocity relative to the microwave background with extraordinary precision, 369.82 kilometers per second, toward a point in the constellation Crater near the border with Leo. At that speed, you would cross the entire distance from Earth to the Moon in about 17 minutes. That motion is the sum of everything. Earth around the Sun around the galaxy through the Local Group, the Local Group falling through Laniakea. Subtract it, and the sky flattens out into near-perfect uniformity, except that something in the data may not be flattening properly. If our motion through the universe is real, it should leave the same signature in more than one place. Moving through a sea of distant galaxies should make them appear very slightly more numerous ahead of us than behind. That prediction is precise, and in 2021, Nathan Seacrest and colleagues tested it, using 1.36 million quasars, the extremely bright cores of distant active galaxies, drawn from the Catwise catalogue built on NASA's Wide Field Infrared Survey Explorer. They measured the lopsidedness in how quasars are distributed across the sky. They found a dipole, but its amplitude came in over twice as large as our measured motion should produce, rejecting the purely kinematic explanation at 4.9 sigma, a chance probability of about 5 in 10 million, and the direction did not match cleanly either. The The quasar dipole points roughly 28 degrees away from the microwave background dipole, two measurements of the same supposed motion, disagreeing in both strength and direction. The response has been vigorous, and it deserves equal weight. In 2024, Abgari and colleagues argued that the analysis underestimated its own uncertainty. The quasar sample shows a known bias tied to how the WISE spacecraft scanned the sky. More quasars catalogued near the ecliptic, fewer near the ecliptic poles. Accounting properly for how a masked, patchy sky couples different patterns together, they argued, widens the error bars enough to drop the tension below 3 sigma, closer to a 1 in 1,000 fluke than a 1 in 2 million one. The counter-response came quickly. Teams running detailed forward modelling simulations, generating mock catalogues that reproduce realistic clustering, masking and noise, reported that the significance does drop from 4.9 sigma to somewhere around 3.3 or 3.6, but that the excess survives. Their conclusion, the anomalously large dipole cannot be explained away by clustering and numerical artifacts alone, and it remains a challenge to the standard model. Nobody has settled this. The measurement is at the edge of what current data can resolve, and both sides are doing careful work. But hold the implication in your mind for a moment. If the anomaly is confirmed, the universe would possess a genuinely preferred direction on scales of billions of light years, a faint cosmic axis, quietly violating the assumption that all of modern cosmology rests on. Even at the very largest scale, the question of whether up exists is still open. So walk the whole ladder back down. Earth gives you a direction, produced by one lump of rock beneath your feet. The solar system gives a different one, perpendicular to a disk assembled from a collapsing cloud 4.5 billion years ago. The galaxy gives a third, tilted 60 degrees away from the second, inherited from a completely unrelated collapse billions of years earlier still. 3 definitions of up, none of them connected, none of them agreeing, none of them extending beyond the structure that made it, and beyond the last of them, a universe that may have no preferred direction at all, or may have one so faint we are still arguing about whether we can see it. Every up we have found is temporary local, and on loan from whatever mass happens to be nearby, which leaves one possibility we have not yet examined. If the universe refuses to supply a direction, if nothing out there will hand us a floor and a ceiling, then perhaps the answer was never to go looking for one. Perhaps we build it ourselves. Every problem so far has belonged to machines. Fuel budgets, plane changes, borrowed momentum from planets that never noticed. But the moment you put people inside those machines, for years rather than months, the question changes shape entirely. Because a spacecraft does not care whether it has a flaw. A human body does. And the evidence for that is not speculative or theoretical or projected. The evidence has been accumulating in medical records for 6 decades, one astronaut at a time. Bone maintains itself by being loaded. Every step you take sends a small shock through your skeleton, and specialized cells read those forces and decide how much material to lay down. Remove the load, and the cells that build bone slow down, while the cells that dismantle it carry on at their normal pace. The result is measurable and consistent. NASA's figures put the loss in the proximal femur, the top of the thigh bone where it meets the hip, at roughly 1 to 1.5% per month. Over a 6-month stay, that adds up to somewhere between 6 and 10% of bone mass gone. To place that, a postmenopausal woman on Earth, in the years when bone loss accelerates most sharply, typically loses in an entire year what an astronaut can lose in a single month. And the loss is not evenly distributed. The weight-bearing bones suffer most: hips, spine, legs, precisely the parts of the skeleton whose only job was to hold you up against a force that no longer exists. Muscle follows the same logic. Postural muscles, the ones in your back and calves and thighs that fire constantly without your noticing to keep you upright, simply stop being asked. The European Space Agency has documented muscle losses of 10 to 20%, even on short missions, with estimates running toward half of total muscle mass on long ones if nothing is done. Then there is the shift most people never think about. On Earth, gravity holds a substantial share of your blood and body fluid in your lower half, which is why standing for hours makes your ankles swell and why blood pressure differs between your head and your feet. Remove the pull, and that fluid migrates upward and stays there. Doctors call it cephalad fluid shift. Cephalad simply meaning toward the head. Within hours, astronauts develop noticeably puffy faces and thinner legs. The heart, no longer fighting to push blood upward against a column of weight, adapts by working differently. And pressure inside the skull rises relative to what the body considers normal. Which brings us to the finding that genuinely alarmed NASA's flight surgeons. Astronauts started coming home with different vision. Not blurred from fatigue, structurally different. Detailed imaging revealed swelling of the optic disc, where the optic nerve enters the eye, folds appearing in the choroid, the vascular layer behind the retina, and most striking of all, flattening of the back of the eyeball itself, a sphere, gently pressed out of shape from behind. The condition now carries a name, spaceflight-associated neuroocular syndrome, and it is not rare. One survey of NASA astronauts after long-duration flight found that 52 out of 64, around 81%, showed at least one ocular finding, with roughly 70% developing swelling of the optic disc. Picture what that means physically. The eye is a pressurized ball of fluid. Change the pressure balance around it, inside the skull on one side, inside the eye on the other, and the softest structure gives way. In some astronauts, those changes have persisted long after return to Earth. The current defense is exercise, and crews take it seriously. Roughly 2 hours a day, most days, on a treadmill with a harness that pulls them down against the belt, a cycle machine, and a resistance device that uses vacuum cylinders to simulate lifting weights. The programs work. Bone loss rates today are far lower than in the era before them. But here is the honest problem, and NASA states it plainly in its own research literature. Exercise reduces the loss. Exercise does not eliminate it. Weight-bearing sites still lose measurable bone even with perfect compliance, and the recovery data is more sobering than most people expect. One study followed astronauts for 12 full months after long-duration flights, measuring bone strength and internal bone architecture in the lower leg. A year after landing, those measures had still not returned to pre-flight values. 12 months on Earth, and the skeleton had not finished repairing 6 months in orbit. Now, scale the mission. A round trip to Mars, under current planning assumptions, involves something in the region of 30 months of near weightlessness, whether daily exercise alone can carry a crew through that remains genuinely unresolved. Advocates point to steadily improving protocols, better nutrition, and drugs already used against osteoporosis, showing promise in orbit. Skeptics note that nobody has ever tested a human body for 30 continuous months without weight, that the countermeasures consume enormous amounts of crew time and station power, and that a crew arriving at Mars too weakened to work would have no way to recover. Nobody knows, and the uncertainty is exactly why the most studied alternative has nothing to do with exercise at all. The alternative is rotation. The physics is simple enough to feel in your own body. Sit in a car taking a fast curve, and you feel pressed against the door. Nothing pushes you outward. What actually happens is that the door pushes you inward, forcing you to follow the curve instead of continuing straight. Your body interprets that constant inward push as a force pressing you outward. Spin a habitat, and the same thing happens continuously. The structure's wall pushes its occupants inward, curving their paths into circles. Physically, this is centripetal acceleration. To the person standing inside, the sensation is indistinguishable from weight. Not similar to weight, indistinguishable. Your feet press against the floor. A dropped cup falls. Water poured from a jug lands in the glass. Your inner ear reports a steady, consistent pull, and your legs feel loaded exactly as they would on a planet. But the geometry inverts completely. Inside a rotating habitat, down points outward, toward the rim, toward the hull, toward the vacuum on the other side of the wall, and up points inward, toward the axis of rotation, which means that if you built a rotating cylinder and stood inside it, the ground would curve upward on both sides and continue over your head. Your neighbors would be standing above you, upside down from your point of view, feeling perfectly normal. Now walk toward the axis, climb a ladder inward, and your apparent weight drops with every step, because the circle you are traveling gets smaller and the acceleration needed to keep you on it gets weaker. Reach the axis itself and your weight approaches zero. Imagine standing at the center of such a place. Push off gently and you would drift, genuinely weightless, inside a structure where, a few dozen meters away, people are walking around at full Earth weight. A single habitat containing both conditions at once, separated only by how far you are from the middle. That is not a design flaw. Engineers consider it a feature, a place for manufacturing processes and recreation that require no gravity at all. But the geometry produces two problems that have haunted every design ever drawn. The first is the gradient. Since apparent weight depends on distance from the axis, your head and your feet do not experience the same pull. Standing on the rim, your feet sit farther out than your head, so your feet weigh more. The underlying physics is identical to what produces ocean tides on Earth, where the near side of the planet feels a stronger pull than the far side, scaled down to the length of a human body. In a very large habitat, the difference across a person's height is negligible, a fraction of a percent, entirely unnoticeable. But shrink the radius, and the gradient grows sharply. In a small spinning structure, you could stand up and feel your head grow measurably lighter than your feet, every second, continuously. The body reads that as wrongness, and wrongness of that particular kind produces nausea. The second problem is stranger and harder to shake. In a rotating frame, anything that moves gets deflected sideways. Engineers call it the Coriolis effect, the same phenomenon that curves weather systems on a spinning Earth. Inside a habitat, it becomes personal. Throw a ball straight ahead, and it curves away from where you aimed. Pour water from a jug and the stream bends, missing the glass. Climb a ladder, and you feel pushed gently to one side. Worst of all, turn your head, and your inner ear reports a rotation that your eyes never saw. A phantom tumbling motion, arriving from nowhere. That last one is the killer. Head movements in a rotating environment generate exactly the kind of sensory contradiction that produces motion sickness in its most miserable form, which raises the design question everything else depends on. How fast can you spin before people stop functioning? For decades, the answer looked settled. Rotating room experiments in the 1960s, many of them run by Ashton Gray Beale and colleagues, along with a 40-foot diameter rotating station simulator at NASA's Langley Research Center, produced a set of comfort charts. The consensus figure that emerged was about 6 revolutions per minute. NASA's Manned Systems Integration Standards, published in 1987, carried it forward. Most people without prior experience can tolerate up to 6 rotations per minute, but become sick and disoriented above that, unless carefully prepared through graduated exposure. 6 rotations per minute became the ceiling that every serious habitat design was drawn around. And that ceiling sets the size, because slower rotation demands a larger radius to produce the same weight. At 6 rotations per minute, generating full Earth weight requires a radius of roughly 25 meters, a spinning structure about 50 meters across, comparable to the length of an Olympic swimming pool. That was the smallest habitat anyone believed was habitable, except the number has since moved, considerably. Later experiments found that people adapt far better than the early charts assumed, provided the spin-up is gradual and progressive. Gray Beale's own work, with James Reason, showed subjects reaching 10 rotations per minute without ever experiencing motion sickness, when the rate was raised in careful increments, and they made deliberate head movements at every stage. 10 rotations per minute drops the radius for Earth normal weight to about 9 meters, roughly the height of a 3-story building. Then, In 2001, Lawrence Young and colleagues at MIT went considerably further. Using a short-radius centrifuge, they found that most subjects could adapt their eye movements and their sense of orientation while rotating at 23 rotations per minute. At 23 rotations per minute, the radius required for full weight falls to under 2 meters, shorter than the person standing in it. The implication for engineering is enormous. Habitat mass scales brutally with size, and a structure that could be 10 or 20 times smaller becomes something you might actually launch rather than something you draw and file away. But treat that result carefully, and the researchers themselves do. The MIT subjects lay horizontal in a laboratory centrifuge for limited sessions. Nobody has ever lived at 23 rotations per minute, and at that radius, the gradient across a standing human body would be extreme, with the head sitting near the axis and weighing almost nothing, while the feet carry a full load. The disagreement remains open. Recent reviews describe the old 6-rotation limit as overly conservative, while acknowledging that the assumptions behind it were never properly validated in the first place, and that the true limits of long-term human adaptation remain undefined. We have been arguing about this number for 60 years, without ever building the thing that would settle it. What makes that especially strange is how long the idea has been on paper. In 1929, an Austro-Hungarian army officer turned engineer named Hermann Potocznik, writing under the pen name Hermann Nordung, published a book in Vienna titled The Problem of Space Travel. In it, he laid out a rotating wheel-shaped habitat about 30 meters across, roughly 98 feet, about the width of a typical city intersection, with an airlock at the hub and living quarters at the rim, spinning to provide weight. He included over 100 hand-drawn illustrations. He suggested placing it in geostationary orbit. He died the same year the book appeared, aged 36. No nation on Earth would put anything into orbit for another 28 years. Then, in 1952, Werner von Braun and Willy Ley published their version in Collier's magazine, a rotating wheel 76 meters in diameter, 250 feet across, 3 decks deep, turning at 3 rotations per minute to produce about 1/3 of Earth's gravity, crewed by 80 people. Those illustrations did something no engineering paper could. They fixed the image of a space station in the public mind for generations. When most people picture a station today, they still picture a wheel. But reality diverged completely. Skylab did not rotate. Mir did not rotate. The International Space Station does not rotate. Every station humanity has actually built has been a non-rotating structure in permanent free fall. The reason is not physics. The reason is difficulty. Spinning a large structure safely, balanced, docking capable, structurally sound under continuous stress, with crew moving mass around inside it, remains substantially harder than assembling a stable one that simply drifts. The most ambitious version came from Princeton. In the 1970s, physicist Gerard K. O'Neill set his undergraduate students a problem: design large structures in space that people would actually want to live in. The results filled his 1976 book, The High Frontier. His largest concept, Island 3, still carries his name. A pair of counter-rotating cylinders, each about 8 kilometers in diameter, 5 miles, and up to 32 kilometers long. 20 miles, longer than the island of Manhattan. Each cylinder divided lengthwise into 6 strips, 3 of habitable ground, 3 of transparent window. Enormous external mirrors angled to reflect sunlight inward, opening and closing to create a day and night cycle, rotating at roughly half a revolution per minute. 1 full turn every 2 minutes, enough to produce Earth normal weight at the inner surface. Population, several million people, now stand inside one. The ground beneath your feet curves gently upward on either side, rises past the window strips and closes overhead. A landscape of fields and towns hanging 8 kilometers above you, 5 miles up, roughly where an airliner cruises. Sunlight arrives through the windows in long, bright bands. And in the far distance, 20 miles away, the end cap, nobody built it. And the reason is not that the physics fails. The physics is sound, and the engineering was studied seriously by NASA's Ames Research Center across a series of summer studies in the mid-70s. The reason is mass. Structures of that scale require material quantities that launching from Earth's surface makes absurd. O'Neill understood this from the start. His designs assumed the raw material would come from the Moon, and later from asteroids, thrown into space by electromagnetic launchers rather than lifted out of Earth's gravity well, which means an O'Neill cylinder is not really a habitat proposal. An O'Neill cylinder is a mining proposal, wearing a habitat's clothes. Strip away the engineering and one insight remains, and it reframes the entire story. Up does not require a planet. Up requires only a consistent force, steady, uniform, pointing reliably in one direction, applied for long enough that a body can build its entire sense of orientation around it. Gravity is simply the most abundant and familiar source of that force, the most convenient, not the only one, because we now know of 3 separate ways this universe manufactures a direction. Planetary mass produces one by pulling everything toward a center. Orbital motion produces another by organizing an entire system into a plane and defining what stands perpendicular to it. And pure rotation produces a third, requiring no mass at all beyond the structure you build, only spin, maintained indefinitely, turning empty space into somewhere with a floor. 3 manufacturers, 3 different mechanisms, all of them real, and every single one is local. Step off the planet, and its version disappears. Leave the disk, and its version means nothing. Drift to the axis of a spinning habitat, and the up you built dissolves in your hands, which leaves the question this whole journey has been circling since the beginning, and it deserves asking plainly now. If every up we have ever found, or ever made, is on loan from something nearby, has anyone, anywhere, ever truly owned one? Before answering that, consider one more discovery, announced only last year, and almost accidentally. Somewhere in the southern sky, about 120 light-years from here, sits a system catalogued as 2M1510. The light we study from it left around 1906, the year an earthquake flattened San Francisco, and has been travelling toward us ever since. At its heart lie 2 brown dwarfs. Brown dwarfs occupy a strange middle ground, too massive to be planets, too light to sustain hydrogen fusion in their cores, the process that makes a star a star. These 2 carry about 3.3% of the Sun's mass each, roughly 35 times the mass of Jupiter, objects that tried to become stars and could not quite manage it. From our vantage point, they pass in front of one another as they orbit, an eclipsing pair, and only the second such brown dwarf pair ever discovered. They circle each other every 20.9 days, slightly less than a lunar month on a noticeably stretched orbit. A third brown dwarf drifts far out at roughly 250 times the Earth-Sun distance, taking about 11,000 years to complete one lap. The whole system belongs to a group of stars called the Argus Moving Group, aged around 45 million years. Young by cosmic standards. When these objects formed, Earth was warm and forested, early whales had recently returned to the ocean, and the Himalayas were only beginning to rise. The astronomers studying it had no interest in planets whatsoever. Eclipsing pairs of brown dwarfs are enormously valuable for a mundane reason. They let you measure mass and radius directly, which is the only way to check whether our theoretical models of how brown dwarfs cool and shrink are actually correct. A team was using UVES, the ultraviolet and visual Echelle spectrograph, mounted on the European Southern Observatory's Very Large Telescope in Chile, to refine those measurements. They were doing calibration work, careful, unglamorous, essential, and in the data, the orbit was behaving wrongly. Every elliptical orbit slowly rotates over time. The long axis of the ellipse, the line joining the closest and farthest points, swings gradually around, like the hand of an extremely slow clock. Astronomers call it apsidal precession, and several ordinary effects cause it. General relativity produces it. Tidal distortion between two close bodies produces it. Every one of those ordinary causes turns the ellipse forward, in the same direction the object's orbit. The team measured two M1510's ellipse turning backward. They quantified the rate and found it detected with 99.7% confidence, fast enough that the ellipse would complete a full reversed rotation in under 4,000 years. Meanwhile, the predicted forward precession from relativity and tides combined came out roughly 100 times too small to matter and pointing the wrong way. Something else was pulling. They checked the distant third brown dwarf. Its effect turned out to be 6 orders of magnitude too weak, 1,000,000 times too small to account for what they were seeing. One possibility remained, and it is one of very few known causes of a backwards turning orbit. A third body, orbiting the pair not in their plane, but nearly perpendicular to it. A polar planet. In April 2025, Thomas Baycroft, a doctoral student at the University of Birmingham, published the result with colleagues Lalitha Sairam, Amaury Triaud and Alexandra Correa in Science Advances. Baycroft's summary was direct. They reviewed every possible scenario, and only one remained consistent with the data. Triaud, his co-author, called it a genuine surprise, noting that the observations had never been collected to look for such a planet or such a configuration in the first place. Of the 16 circumbinary planets known before this, planets orbiting both stars of a binary, every single one shares the plane of the stars it orbits. Everyone lies flat, like ours. This would be the first strong evidence of a world travelling over the poles instead. Around a pair of failed stars, 120 light-years away, a planet may be doing precisely the thing our entire solar system makes prohibitively expensive. Now the honest caveat, because this detection is not a photograph. Nobody has seen 2M1510 ABB. The planet is inferred entirely from the motion it induces in the 2 brown dwarfs. Dynamical reasoning, not direct imaging. And in a system that faces us this way, the planet's own back-and-forth pull produces no measurable Doppler signal at all, which means the usual confirmation route is closed. And the challenge has already arrived. In late 2025, a separate team published a new photometric timing analysis of the same system and reported that the recent orbital solution from the Doppler data appears inconsistent with the existing eclipse photometry. Their assessment was blunt. A timing offset in the velocity data may have produced a spurious signal mimicking retrograde precession, and the claimed planet may be a false positive. The original team's case rests on eliminating every alternative. The critics' case rests on a mismatch between 2 independent datasets. Follow-up observations will settle it, and until they do, the planet exists as strong evidence rather than confirmed fact. But the underlying physics stands regardless of whether this particular planet survives scrutiny. Astronomers have already observed polar-aligned circumbinary disks, flat sheets of gas and dust orbiting binary systems perpendicular to the stars themselves. And a planet forming inside such a disk would end up on a polar orbit automatically, for free, with no energy expended at all. Which reframes this entire story in a single sentence. Physics does not forbid polar orbits. Physics forbids reaching them from inside a flat disk. Born there, you live there effortlessly. Born here, you cannot afford the ticket. Come back to our own system and consider the most favourable set of circumstances humanity has ever been handed. In the late 1960s, NASA scientists realised that once roughly every 176 years, the outer planets cluster on one side of the Sun in an arrangement that lets a single spacecraft chain gravity assists from one to the next, Jupiter to Saturn to Uranus to Neptune. That alignment happened in the late 1970s. Miss it, and nobody alive would see the next one. It will not return until the 22nd century. Voyager 2 launched on the 20th of August, 1977, and spent the following 12 years doing something no spacecraft has done before or since. Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in 1989. 4 giant worlds, each one's gravity used to reach the next. A journey that would have taken roughly 30 years on engine power alone, completed in 12. And here is what that once-in-2 centuries opportunity brought, in terms of direction. Outward. Always outward. Every assist bent the trajectory within or slightly across the plane, never meaningfully out of it. The steep angle Voyager 2 eventually acquired came from encounter geometry at Neptune, not from any decision to climb. The most favourable planetary arrangement in 176 years, exploited perfectly by some of the best trajectory designers who have ever lived, and the disk still dictated where the spacecraft went. And yet, bolted to the side of each Voyager is something that has nothing to do with orbital mechanics at all. A 12-inch gold-plated copper phonograph record, 115 images encoded onto it. Greetings spoken in 55 languages. The sound of wind, of rain, of surf. Whale song, a human heartbeat, music from across the world, instructions etched onto the cover explaining how to play it, and a diagram showing where in the galaxy it came from. Curated by a committee led by Carl Sagan, assembled in a matter of weeks in 1977. Think about the arithmetic of that decision. Nobody involved believed a recipient was likely. Nobody expected the record to be found. The realistic probability of any intelligence ever encountering either spacecraft is, by any honest estimate, vanishingly small. The coldest, most ruthlessly optimized orbital mechanics ever executed by our species, a mission that traded entire planets for fuel savings, still made room for a letter with no expected reader. Both Voyagers now travel far beyond Pluto's orbit, in interstellar space, carrying that record. And both of them are still moving on trajectories written by the plane they were launched from 4.5 decades ago. One asymmetry remains, and it may be the strangest detail in this whole account. Step outside on a clear night in the northern hemisphere and find Polaris, the North Star. It sits almost exactly above Earth's rotational axis, so as the sky wheels overhead through the night, Polaris barely moves. Every other star circles it. That single fact anchored navigation for nearly every civilization that ever crossed open ocean or empty desert. Find Polaris, and you know north. Measure its height above the horizon, and you know your latitude. Whole mythologies were built around the star that stays still, except Polaris is an accident of timing. Earth's rotational axis does not hold steady. It traces a slow cone in space, completing one full circuit in roughly 26,000 years, the same wobble you see in a spinning top as it slows, which means the pole star changes. Around 5,000 years ago, when the Egyptian pyramids were being built and aligned to the sky, the pole star was Thuban in Draco. In roughly 12,000 years, the honour will pass to Vega. Polaris is simply the star that happened to be standing there during the particular window when human civilization learned to navigate. Now look at the other pole, the north ecliptic pole, the solar system's own true vertical, the direction this entire story has been about, sits in a faint stretch of Draco, tucked between 2 moderately bright stars. Nothing marks it. No beacon, no guide star. Nothing you could point to and name. Astronomers know exactly where it is, to fractions of an arcsecond, because they calculated it. But no ancient navigator ever used it, and no mythology was ever built around it, because there has never been anything there to see. Earth's up came with a marker. The solar system's up came with nothing at all. But the disk itself, the plane, the structure, the thing that cost so much to leave, that you can actually look at with your own eyes. Find a genuinely dark sky, well away from city light. Go out about an hour before sunrise, or an hour after sunset, and look toward where the sun is hiding below the horizon. Under the right conditions, a faint cone of light rises from that point, tilted, tapering upward into the sky. Soft, silvery, easily mistaken for the first hint of dawn arriving hours early. Many cultures called it exactly that, a false dawn. The explanation came in 1683 when Giovanni Domenico Cassini published the correct account. What you are seeing is sunlight, scattered off countless grains of dust orbiting the sun. Not atmosphere, not distant stars. Dust, particles ranging from a few micrometers to a few millimeters across, ground out by asteroid collisions and shed by disintegrating comets. The detailed picture of where that dust comes from took another 3 centuries and infrared satellites to map properly. But here is the part that matters. That dust obeys the same rule as everything else. Produced by objects in the plane, it stays in the plane, concentrated into a lens-shaped cloud centered on the sun, thin compared to its width, which is precisely why the glow appears as a narrow, tilted band rather than a general brightness spread across the sky. Stand under it, and you are not looking at a curiosity. You are looking edge-on, with unaided eyes, directly along the plane that has governed every mission, every trajectory, and every argument in this entire story. The structure is visible. We just never recognized what we were seeing. So where does this leave the future? Every serious proposal to reach high solar latitudes runs into the same wall and gives the same answer. Fly out to Jupiter and let the giant do the turning, or spiral inward past Venus, taking a little more inclination on each pass, climbing a staircase built out of other planets' gravity. Borrowed momentum, incrementally applied. Nobody has found a way around it, because the arithmetic does not permit one. What may genuinely change is propulsion. Electric thrusters keep improving, quietly, incrementally, in ways that compound over years of continuous operation. Solar sails remain the most tantalizing possibility on the table, and also the least proven at the scales these missions demand. What will not change is the other half of the equation. Chemical rockets are not going to become fundamentally more efficient. They are already close to the limits that chemistry allows, and 29.78 kilometers per second is not going to become cheaper to cancel. That number is set by Earth's distance from the Sun and by the Sun's mass. It has not moved in 4.5 billion years, and it will not move for us. Which brings everything back to where this started, and to a picture that is now complete. Earth's up comes from mass, one planet, pulling everything toward its center, defining a direction for anything close enough to feel it. The solar system's up comes from motion, the orbital circulation of a disk that flattened itself 4.5 billion years ago, defining a perpendicular that nothing living has ever traveled along. And a habitat's up would come from spin, a direction manufactured out of nothing but rotation, maintained indefinitely, requiring no world at all. 3 separate mechanisms, all of them real, all of them producing a genuine, measurable, livable direction, and every one of them local, every one valid only while you remain inside its reach. So here, finally, is the direct answer to the question this began with. Going up in the solar system is not impossible, because something blocks it. Nothing blocks it. The direction is empty, open, and physically unremarkable. Going up is effectively impossible because of what it costs. Turning 90 degrees out of the plane demands roughly 42 kilometers per second of velocity change. More than 3 times the 12.3 kilometers per second required to escape the sun's gravity entirely and leave the solar system forever. It costs more to turn than to leave, and the reason is a single inherited number. Everything launched from this planet carries 29.78 kilometers per second of sideways motion that must be erased before any climbing can begin. Not reduced, erased, and then rebuilt in a new direction from the same fuel tank. We never escape the disk because we were born inside it, moving with it, and the price of stepping off is the price of undoing 4.5 billion years of shared momentum. Tomorrow, you will stand up. Your feet will find the floor. The pressure will arrive in your souls exactly as it always has, and your inner ear will settle, and your eyes will confirm what your body already reported, and you will know, without checking, without wondering, without a moment's doubt, which way is up. That certainty did not come from the universe. The universe does not issue directions. That certainty was assembled by a specific and improbable history, a cold cloud that happened to be rotating, a collapse that concentrated its spin, collisions that ground away everything moving vertically until only a thin plate remained, and one particular lump of rock and iron that gathered inside it and has been pulling on you ever since. Not a law, an arrangement, local, temporary, and entirely dependent on where you happen to be standing. You never owned it, neither did anyone. We are all of us holding a direction on loan from whatever happens to be pulling nearby for exactly as long as we stay close enough to feel it. You have been held your entire life, not by a law of the universe, by one particular planet, 4.5 billion years old, that gathered itself out of a flat sheet of dust and has been pulling on you ever since, through every night you couldn't sleep, every room you walked out of, every moment you were certain you were alone. It never once asked to be noticed. That is the strange kindness buried in all of this. Up is borrowed, yes, but alone means something is still lending, and this one has never stopped, not for a second of your life, not for a second of anyone's. The Babylonian watching the zodiac, the carpenter trusting the bubble in a level, a child pulling herself upright for the first time and discovering, without being told, which way the world goes. The same answer. None of them ever met. Tomorrow morning you will stand up and the floor will meet your feet exactly as it always has. Nothing will have changed, but now you'll know what's underneath it. Something has been holding you the whole time. Thank you for staying with me through all of this. If tonight meant something, a like and a subscribe is how you tell me. More journeys are coming, quieter ones, stranger ones. I hope you'll be here. Sleep well tonight. The ground isn't going anywhere.